Bye-bye. Okay, good afternoon, everybody. Oh boy, the waiting room. Uh, okay, just a moment. Anna, are you in?
Yes.
Okay, great. Can you handle I inadvertently put on the waiting room. Let me see if I can promote you. Uh, Here we go. Okay, you're now a co-host. Yasmin, are you in? Okay, very good. I'm going to promote you to be a co-host as well. All right. Okay, everybody. Thanks for coming. I want to keep the chat open. We just keep the general chat open. I don't want to. I'm going to mute everybody, and I don't want people trying to share their videos. So anyways, welcome everybody. I'm going to go to the, hold on a second. Okay. I'm going to go to look at our Keynote file. We'll talk about a few things. So here we go. Okay, can everybody see the opening slide of the Area 51? Okay, good. I can see that. All right. What we're going to do today, we're going to try to do every day is, where should you be by today? And I'm going to remind you about exam 3, that's next Tuesday. The big thing that we're going to do today is look at a physics simulation website that I've been using in some of my other classes, and I think it's a good point to turn you guys loose on them. There's some really interesting things, and it'll be mostly with the idea of vibrations, oscillation, and waves, sound waves and light waves and stuff. So we'll mostly be doing that. And we won't be doing any homework review today, but on Thursday, yeah, we'll review some homework, including this one here, which I believe is in homework 15. Okay. So let's go to where should you be today? All right, here's the YouTube diversion page. And, oh, you know what? Is this, yeah, we're being recorded. Okay, good. This is the YouTube diversion page. This is where you should be today. You should be either already or later today listening to this lecture in YouTube. And also, after that, you'll be ready to tackle homework 15. Now, don't forget to get going on your homework, right? Do not leave it for the last minute. Don't leave it for next Monday night, right? Get some of it done this week, right? And to stay on track, lecture 23, then you can see down here a little lower down, lecture 24, that'll be your waypoint for Thursday. And homework 16 will be, well, it's activated right now, but if you're pacing yourself, that'll be a good time. And then lecture 25 would be next Tuesday if we were going to have a lecture in the lecture hall, but we'll have our exam online instead of in the lecture hall next Thursday. All right, so let me pause for questions and go ahead and type in a question. Not John, not really. They're not specifically for that. In other words, there's a little bit of low overlap on homework, but I'm releasing them. Remember, we're using the stuff from last spring that we recorded in the lecture hall, and so I'm releasing them just the way in the same sequence that I did last spring. So that's why they partner up. And you know, sometimes I don't have a homework assignment every day. Every once in a while, I don't have any homework. But in spring of 19, this is the sequence that we are on. Okay, is the exam just on Canvas? Yes. Dana, it's a lot like a big homework assignment, except you only get one shot, and you have a specific amount of time. I believe it's set for 70 minutes. But you can take it all anytime during the day. So you can take that 70-minute block of time and schedule it early in the morning, you know, like at 9 o'clock, right at lunchtime, right after dinner, 7 p.m., whatever you want to do it, as long as you get it in by 11:59 p.m. Next Tuesday night. Now remember, all of our homework is due 11:59 p.m. next Monday night, so do not let me catch you napping on homework. Will there be an SI session to study for the exam? Yeah, but you're gonna have to check in with Miss Yasmin on that one, but I believe she's got stuff scheduled for you. And so yes, Comfort, we're gonna be tackling the last 3 chapters, and I've got some more stuff to add to chapter, I believe it's chapter 8. So you can see that when you get in there, you can see that there's some gaps and stuff. Okay. Yaz is scheduling one right now, so that's good. All right, great. Let's talk. I'm going to stop sharing this, and I'm going to start sharing my Safari windows. All right, and so let me pause for just a second. And actually, let me try doing one more thing with you. Okay, so this is the website that we're going to visit in about 2 seconds. And we'll trot through some of the simulations so you can kind of get a feel for, how they work and stuff. And this, don't worry about copying down the link. It's already linked in web courses, okay? So now, let me stop sharing that. And let me get my, hold on, let me just get my, okay. Let me get my Safari window to the sharing spot, and here we go. Okay, here's the simulations page. This is the one that links to the home page. And these are all different kinds of physics simulations, and we'll actually do a few of them. Can you all see this physics simulations page? Okay, great. You guys can see it. All right. I always have to check. I shouldn't be so paranoid, but anyways. So the ones that I want to go and look at, they're down here. Let's see. The first one is, I mean, you can mess around with all of them, but the ones that I want you to mess around with are this one, masses and springs, and then actually either one of these two, masses and springs basics and masses and springs regular. Now you see this little S here, or I guess that's the letter 5, or the number 5. That means that it's using Flash, and so you have to have Flash installed on your computer. All right. Now here's masses and springs basics. Can everybody see that now? Okay, good. Now take a look at how this works. Okay, you can download these onto your computer and run them. They're Java applications, but these ones you can actually run inside your web browser. Now I'm in Safari, and it works pretty good in Safari. You could try it out in, Firefox or Google Chrome. So you have this set of 3. Let me move my chat window out here. 3 different windows, and here's a lab over here. Actually, I haven't tried this one, so let's try to look at this one. Okay, so over here, one of the factors of a string or of a spring system is that it'll stretch a certain amount of. So let me stop that. It'll stretch a certain amount under a given amount of pull force. Okay, so here's the position where the spring would be if it weren't stretched, or if it weren't loaded up with a weight. Okay, and then the resting position, let's put that weight back up on there. Okay, and so this thing's going to eventually dip down to, let's see if we can get it to stop there. Right, so that's where it eventually stops oscillating, stops vibrating up and down. Okay, and you can change this, the weight, I guess. All right, and notice when you put more weight on it, it pulls the mass down a little bit further. Okay, and you have a new position. Now, one of the things that's pretty nice about this is that you have a ruler, I believe, right here. So you can move a ruler over here, and you can kind of measure the distances here. Okay, so here's where the spring would be at its equilibrium position, and that's 30 centimeters. And then this one, this weight of 150 grams stretches at about 54.5 or so. So we'll call that to the 54 centimeter mark. And so that tells you that your total stretch is 24. Okay. So let's take this off and put it back over there. So there it is, unstretched, just kind of sitting there. And let's see if we can make it a little bit. Let's put it down to 100. Okay, so that'll stretch it down there. And so you can see with only 100 grams, it goes down to about 46. So a total stretch of 16 centimeters. Okay, and it will oscillate about this point if you let it oscillate. All right, and you could put in these different things here. Let me see what this movable line is. No, let's just let's see if we can do it again. All right, now we've got these other things turned on. Okay, so you can see the yellow acceleration vector, and you can stop it at any point that you want. Okay, there's also a timer over here, so you can mess around with it. Okay, and I'll just point out to you that you can try out these other ones here. This is the bounce simulator. This is the stretch simulator. So you can what you want to do with this is just kind of fool around and see what happens. Maybe take a few notes, do some mental experiments and stuff. All right, now let's take a look at the waves intro. All right, and let me ask you again, can you see the waves page? Okay, great. All right, so this is going to be same thing. This one will load in the browser. Okay, and this one, I believe this one has a few variations. Water waves, sound waves, and light waves. So let's take a look at sound waves. And this will show you just like an overhead view of the pressure waves that we know as sound. Okay, and so let's, you'll be able to play the tone. I don't know if you guys will hear this or not, but let me bring the frequency up a little bit here. And let's, okay, so you go to the green button over here. Okay. Can you guys hear the sound? Okay, when you guys do it yourself, you'll hear the tone. Okay, and when you bring the tone down, you'll hear that it's a little bit lower note. Okay, it just sounds like a computer tone, like a synthesizer. All right, and so you can mess around with the waves intro. Now there's another one called waves interference. Okay, can you see the wave interference screen? Okay, great. All right, so let me move my chat window over here to the side. And okay, so here's the 3 sets here. And this one is really important for us because it actually is going to be important in for the rest of the semester, this whole idea of interference of waves. And what interference of waves means, let's see, here are, okay, this is water waves. So this is the waves that you would see if you're dripping water or dropping waves into a pond. And you can see that, that they form this weird pattern of light blue alternating with black. Now, that is not as interesting to me as the sound waves. Now, sound waves interacting, you can move these things apart. Okay, so there's maximum separation. And again, on this one, you can choose the frequency. And the higher the frequency, the smaller the wavelength, as you'll see. And then you can turn each of the speakers on. Okay, and this is simulating sound waves. Now, the thing that I want you to look at here is the fact that right down here through the middle horizontally, you see alternating patches of dark and light. Dark, now that's not light waves, that's sound waves. So the dark would be dim sound, at whatever tone this is. Let's see, this one doesn't let you turn on the sound. So anyways, this would be right here down the middle, symmetric between both speakers. You have a dim or a faint sound, loud, faint, loud, faint, loud, faint, and going all the way out right down the middle. Okay. Now, if you dip right above that, you'll see the same pattern, except it angles a little bit upwards. So here's loud, here's faint, loud, faint, loud, faint, loud, faint, and it's kind of dipping upward at an angle. And then if you go above that, here's another pattern. Faint, loud, faint, loud, faint, loud. And that is the diffraction of sound, or the interference of sound waves, right? And so this one in the middle, this is why if you have a stereo system at home and you have big speakers, you want to be sitting, the best place to sit is right down here, halfway, out in the room somewhere, but halfway between both speakers, right? And you can mess around with this. Now, I want to go back to to look at the light. You could do the same thing with light waves. But now what I want to do is look at this. We're going to look at slits. And these are going to look very much like the two speakers. Now, I'm going to put two slits in a barrier. Okay, now and I'm going to switch to sound. Okay, so choose two slits. Okay, so here's what two sound waves a single sound wave would look like as it goes through two openings in a wall. Okay, now let me start this. Right, here they come. Now look, as they go through those openings, you start to get the interference pattern. All right, now I'm going to move this gap here a little bit closer, and I'm going to make these a little bit smaller, and I want to make them a little bit closer, and I'm going to increase, I want my frequency good and high, and what that does is it makes the wavelength smaller so we can get more waves into this diagram. All right, so here's the sound generator. Oops, here it goes. Okay, and now you can see that same pattern, all right, that same interference pattern. But right here in this upper slot, you don't have you don't have a speaker there. You just have an opening. Right down here, it makes you think of another speaker down here as well, like the previous one that we did. But it's not, it's just an opening in this wall. So that's why we call this, these wavelets over here, they're as if they're generating a new source of waves, in this case, circular waves. And you can see here's the faint, loud, faint, loud, faint, loud, faint, all the way down the middle. And then here's another one, kind of tilted upwards, very loud right here, close to the gap, faint, loud, faint, loud, faint, loud, right? And you got a symmetric one down here, dipping below that. Now you could fool around with frequencies and amplitude. Let me see, let's try this one. Okay, so now, so these are a little bit not as loud, so they don't get so bright white. Okay, but that's all right. Now, here's the one that I really want to focus on, right? And this is the generation of light going through a system here. Now let's put this down here in the red, and let's do double slit. Okay, and let's make them fairly. Let's see how this one looks. Okay, so here comes the light. Okay, here come the light waves. All right, and so again, oops, let me do that again. You can see the interference patterns forming. Let me move this a little bit closer. Okay. Now we can see a lot more of the pattern. Okay, and so down through the middle here, now this would not be sound waves, so you wouldn't say faint and loud, you would say dim, bright, dim, bright, dim, bright, or even dark, bright, dark, all the way down the middle. Then here's another pattern going up, slanting up to the left here. Here's another one slanting down to the left, down to the bottom. Now the thing about this is, to figure out the exact directions, you need to use a little bit of trig, and we're not going to do that. But it's not a whole lot more than Pythagorean theorem, but it does involve a little bit of trig. Now let's change the wavelength. Now blue is shorter wavelengths, so let's try blue waves here. Right, here come the blues. All right, and you can see that this forms a different pattern, right? And in fact, the smaller the wavelength, let's jam this all the way up to the top frequency, right? Those purple ones, they just kind of go straight through. They don't really form much of a diffraction, of a interference pattern, all right? I guess they kind of do a little bit. But if you were to use an even smaller wavelength like ultraviolet, you'd see an even different pattern. All right, now the next one that I want to show you is, let's see if I can go to the next tab. Let's see. Okay, I'm going to dip out of this one. And oh no, I don't want to dip out of that one. Let me go and start that one again. That's down here in waves, all the way down towards the bottom. Wave interference. Okay, can you see the wave interference page? Audra Spence, yeah, it does mean that the best place to stand is still in the middle. But a lot of times we use this wave interference to, with lasers and stuff anyways, to analyze all kinds of elements and stuff. Okay, good, so you guys can all see this. Let's see, the one that I want to show you now is diffraction, and this one is extremely important. All right, so that's this one over here. So you can fool around with any of these four. This one's the most important one. Now, one of the things about diffraction is when you send light through any kind of a gap or anything that has an edge or a boundary, the light is going to interfere with itself and kind of bend around the gaps, and you're going to get that wavelet phenomenon where it looks like you have two speakers. All right. Now, this one is light, and what I'm going to show you is what the pattern of alternating bright and dark spots looks like to you. All right. If you turn on a laser. Now we're going to go up here to 656, so that's up here. Now, let me dip that down to 6. Okay, now 656, that's the color of a very special wavelength called H alpha that we'll talk about in the next week. All right, now let's zoom some light. Okay, so we're zooming light, a laser beam, into this barrier with a circular dot in it. Okay, and we can make the dot bigger if we want. And over here on the screen is what you would see if your eye was over here. This is what you would see. Okay, you'd see a central bright spot, and then you'd see a ring of brightness and with a dark ring in between. So as before, this is like looking at it in 3 dimensions now. Okay, so if you have a circular aperture, circular opening like this, you'll see circular shape in the diffraction pattern or the interference pattern. Okay, the wave will interfere with itself. Now let's change to a square opening. All right, now that's what square openings give you. Okay, you get the diffraction bars to the left and right, and up and above and below. Right. So a lot of times you can tell the shape of the object, even if you can't see the object, if it's too small to see, but you can see the diffraction pattern, you can tell the shape of the object. Now here's a combo. This one's kind of interesting. All right, so this is a combo of a square and a circle. All right, so let's do a little experimentation with this. All right, now the bigger I make the circle diameter, the more that looks like a circular diffraction pattern. But I've got those kind of stripes in there, and that's from the square. Now, if I turn the square all the way off, like, no, I guess you can't turn it all the way off. Okay, so let's put it back to 0.04. All right, and let's put this back to 0.05. All right, and now let's make the square really big. Okay, now if you have a big square, you can see that the diffraction pattern looks a lot more like a square, but that other stuff in there, you can think, I probably have a circle in there somewhere, right? So they're offset, so this is an example where you can actually tell if you study the trig of, measure it all carefully and do the trig and stuff, which is extremely difficult, way past even physics majors. You could figure out the size and shape of the square and of the circle. Now, here's another opening. This is like a lattice of circular holes, so 4x4 grid. And look at the diffraction pattern over here. This one again, you can tell the lattice spacing by analyzing the diffraction pattern. So you can't, here's an example of this. If you shine not red light, but an X-ray into a crystal, like a crystal of salt, sodium chloride, that's got a cubic shape, and it would have openings, something like this, openings and gaps and barriers, something like that. You would be able to see a diffraction pattern that looks this way. It would be a black and white image, not red, because you can't, we don't have color perception for X-rays, but it would look similar to this if you're doing this for a crystal. And that's why we frequently use X-rays to study the shape of crystals. Okay, now let's take a look at this disorder. So that means it's a little bit blooped up. All right, I'm going to turn off disorder. I don't want to psych your minds too badly. But let's make the lattice spacing, let's change the lattice spacing a little bit more. Okay, so now you can see that it looks more like it looks more like a bunch of circular patterns. Okay, and let's dip the lattice spacing back down. Let's tighten it up. Now it looks more like just a plain old lattice, but down here in the middle you got that square, almost a square pattern. So there's a lot of fooling around that you can do with this. Now the last one I want to show you here is this one. This is the important one. And this is a picture of a person holding up their right arm and facing you. You would call this a complex image. And you can see that in this complex shape, very complex shape of openings, you get this very unusual pattern over here. But now let's rotate it and see what happens to the pattern. See the so there's 90-degree rotation. The person is now horizontal instead of vertical. And I've got the diffraction pattern I had before, but it's sideways, right? And so let's make the person bigger. Okay, and you can see that the diffraction, now it's a strange diffraction pattern, but if you analyze it carefully, I mean, this would be extremely tough to figure out from this diffraction pattern over here that this is, a person holding up their right hand and facing towards you with their other elbow, with their hand on their hip. That would be hard to discern from this diffraction pattern, but you'd be amazed what you can do. So this is the most important of all the demonstrations. Now the last one that I want to show you is wave on a string. Okay, can you see the wave on a string page? Okay, great. All right, now this one's not too fancy, all right, but you can, you could try some of the things with this one. And here's just a string approximated as a string of dots. Okay, and let's just let's oscillate it. Okay. Oh, let me just I'll manually oscillate it. So there's me sending us a wave across this string. And if you do it right, you can set up standing waves. Now that's just me manually doing that. Now here's an oscillator doing it, right? You can change the frequency, make it faster, right? And study what you got and stop it and look at it, stuff. And there's a ruler that you can use here. So you can use that to study things. Another interesting thing is this idea of damping. Okay, now there's a little bit of damping here, right? That means you lose energy as you go from the source of the oscillation to the right. So the wave is not as deep here as it is above the line right over here, right? So with a little bit of damping, that's what you get. Now the other thing I want to show you is you can do it with one loose end. In other words, like it's tied to a frictionless pole, and things work a little bit differently there. And then you can tie it to no end at all. In other words, it just goes on out the window. Okay, and so now the reason I want to show you that is because I want to dial up the damping. Let's put it up to halfway. All right, now look what we got. You barely have any wave energy going out that window, right? So that tells you what damping does. all right? Even if you have plenty of energy over here at the source, by the time you're going out that window, nah, you're basically toast, all right? Now, let me pause and stop sharing that and get back to the keynote, all right? And we'll start uh, playing the keynote again. All right, now can you see my, uh, this is the last page that we were on. Can you see it? The simulations at University of Colorado. I see I got several new messages. Okay, great. So let me click out of there. Now, so that's the website. And as I mentioned, it is, oops, I'm going backwards. All right, so it's linked to the homepage. So you can click into it and look at stuff. It's good. Now, this picture is probably the most important photograph ever taken. And this is why I wanted to show you that lady with her right hand up and facing toward me in the diffraction simulator. And it generated a very complex pattern. Now, this pattern is not as complex, but this is a very, very famous, the very first photo that we made uh, of DNA. This is the X-ray diffraction image. It's complex. You know, you can't really guess very easily what the shape is of the DNA molecule. But they did their trig and they did all their calculus and stuff, and they figured out that it's a double helix from this image. And so a lot of people call this the most important photo ever taken. And it's a diffraction of X-ray images. And so that is why I want you to really play around with that stuff and just try stuff, okay? And enjoy your time with the simulators and just try different things. And if you see something cool, tell your classmates about it, or share something in discussions. All right. Now let's get back to exam 3. I'll let you do all those simulations on your own. That'll work good. One thing I want to point out to you on exam 3, this is what it would look like if you tried to click in there right now. And right now it says there's one question on it. Just to remind you, that's a placeholder question, and I artificially set it to 50 points. You'll have 40 something questions on there, but it'll still add up to 50 points. Okay, so just like I always tell you in lecture, you know, I don't write the exam until I'm done with the last lecture before the exam. And so I always tell you, well, I haven't written the test yet, but it'll be 40 something questions on Scantron and then a couple questions on iClicker for calculations. Now, we're not doing iClickers today, so it'll all be inside web courses. But you might have a 2 or a 3 point calculation in there. You know, like something like a heat melt heat calculation, or maybe even a bonus point calculation for thermal equilibrium, right? So, and also the matching, formula matching, that in web courses, that counts as one question. So if you have 4 matching items, it'll be one question, but 4 points. Okay, so the question number here is going to change, and it might be, you know, 38 or 42, but it'll still add up to 50 points by the time we get to the exam itself next Tuesday. All right, so that is that. Now let's take a look at chat and go ahead and ask any other questions. Antonio, I don't know if it's going to be 2 questions or 1 or 3 or what. And sometimes, you know, we have the easy calculation questions in multiple choice, but usually I have 1 or 2 in there on a midterm. Yeah. Type in another question. Ooh, we're running a little bit long today. That's all right. Any other questions on the exam? Okay, Gordon Campbell. Good. I'm glad to see all you guys in here. Chidima, good. Jenna, good. Audra, very good. Hannah and Taylor, very nice. Okay, if there's no other questions, then we'll close the meeting and I'll put this into YouTube directly. And, uh, and I'll see you guys on Thursday.